Hi everybody, my name is Camden Robertson. I'm here to talk to you about this cool network traffic classification using AI project I did for one of my classes. So we could start by who I am. Like I said, I'm Camden Robertson, third year CSEC major. I did my last co-op at this small insurance company called AmTrust Financial. It's pretty cool. I did security engineering there. Historically, I've been a big Linux blue teamer, but I'm dabbling in red team this year. It could be pretty crazy. I'm a big fan of the Scratch programming language, making education accessible in all forms. And lastly, I like to snowboard in my free time. So let's move forward, shall we? Let's go over the agenda. We're going to talk a bit about what machine learning is. I'm here to make it very digestible, so even freshmen, you got to keep your eyes open. This one's for you. I'm going to talk about what my assignment was and the things I needed for it. Then I'm going to give you guys a little demo. It's going to be cool. Alrighty, let's get started. So some questions are very easy for both humans and computers to answer. One of these such questions could be something like 5 plus 6, right? We all know it equals 11. And it's not that deep. It's pretty simple. Now, the reason why it's so simple is because we've got very clearly defined inputs, functions, and outputs. We know what's going into this addition problem. We know what we're doing with our two numbers, but we know what comes out. Now, some questions are easy for us humans, but they're not very easy for computers. They might be very arbitrary, very opinion-based questions, or so we think. Now, think about a burrito, right? What are some ingredients that could make a good burrito? Things such as steak, perhaps some salsa, or maybe even Sour Patch Kids. No, I'm joking. That would be a terrible burrito. But, it's very obvious for us to tell that Sour Patch Kids in a burrito would not be good. I always say, you got to try everything at least once. I'm going to tell you, you can skip this one. It's not going to be good. So let's go back to kind of our diagram that we had before, right? Where we're going over our inputs, our function, and our outputs for this slightly more complex problem. We still got our inputs, right? We got steak, we got salsa, we got Sour Patch Kids. Our function is the burrito, or more so, what would make it a good or not good burrito. And of course, the output here is not good, right? But the reason why this is so hard for computers to figure out is because it's not really clear what is a good burrito. What I think is a good burrito might not be a good burrito for you. I bet you somebody in the crowd even likes the Sour Patch Kids burrito. It's really messed up. So let's go a bit deeper, all right? Like I said earlier, the problem comes down to the function. If the function's not clear, the computer's going to have a hard time figuring out what to do with its inputs. Think about it, right? What if the function is asking, what makes a good burrito? What if the function is asking, is this network traffic malicious? What if the function got Hennessy? Now, if you guys think about that movie, it was Hitchhiker's Guide to the Galaxy. There's this crazy supercomputer in there, and they ask it this question. They're asking, what's the meaning of the life, the universe, everything? And it says 42, and everybody's freaking out because holy crap, that's the meaning. But then everybody's like, wait, what's the question of life? And it doesn't tell them. It's really messed up. But that's kind of a similar problem to what we have, right? So in normal math, right, we're taking a function, and we're putting our inputs in there to get our output. These are very defined things. For example, if we're adding 5 and 6, it's going to be 11. That's our output. And we know that because we've got our function, our inputs, and what to do with these inputs. However, we come into a sticky situation, and we have the inputs and the outputs, but we don't know what the function is. What are we supposed to do with these inputs, and how do they turn into the outputs? So for example, say we only have the inputs of 5 and 6, you have the output of 11. We got to think, right? What are we doing with these inputs to get us to 11? And we can think about it real hard and we'll say, oh, well, that's addition, right? You add 5 and 6 and you get 11. But sometimes it's just not that clear. What this is called right here, big word of the day, function approximation. Function approximation is when we're taking our inputs and our outputs, and we're figuring out what that function really is. Now, si volvemos al problema del burrito. If we return to the burrito problem, all right, we can come up with a large set of inputs and outputs, right? Think things that can go into a burrito and whether it's good or not good. right? So steak, salsa, Sour Patch Kids, it's not good. Don't try it. Steak, salsa, rice, chicken, beans. These could be good. These could be good burritos. Give them a thumbs up. Chicken, cheese, and marbles. Nobody's eating marbles in here. I'm guaranteeing you that. That's not a good burrito. These are very clear things to us, like I said, not to the machine. So what do we call this? This table we made right here. Our inputs and our output. This is going to be called labeled data. It's very important for a machine learning algorithm later on. Alrighty. Now, you might all be thinking, what's the function that makes a good burrito? And I've got something behind me, and I don't want you to read that. None of you are reading all that. I used AI to write this definition behind me. And it's a solid definition. It's okay, but it's not worth reading. It's not worth your time. And the main thing with the definition of what makes a good burrito, it's going to change every time you eat a burrito. You might eat the best burrito you ever had, and you're like, well, that's what makes a good burrito. You might have a terrible burrito, and you're like, it's not going to happen. But like, there's some clear things we can point out, right? Your burrito has got candy, it's got like solid objects like marbles, it's not going to be good. That's just clear. So we got some defining principles just like that. So using this new knowledge, let's move on to what my assignment was. I'm taking CSEC 520, Cyber Analytics and Machine Learning. I think Joe's in my class too. Shout out Joe. But it's a pretty tough class. I'm taking it with Dr. Bo Yuan. And this was our first assignment. He gave it to us like 2 weeks in. And this is it. This is all he gave us. So we were like pretty scared. We had to read this big paper about intrusion detection on traffic classification and AI. Step 2, we had to make a deep neural network. Like that's all the instructions he gave. It was so open-ended. Then we had to compare and contrast. Now the main thing I was worried about was this. Like this is the instructions for what I'm about to do. And it's just like, wow, my teeth were chattering. It was a real scary thing. But no fear, we figured it out, and I'm here to show you how I did it. Now, I know this looks scary, guys. I know this looks scary. Let me show you what's going on, though. So the model I used, notice how the assignment called for a deep neural network. All right? You've got a neural network here. We're using something called a multi-layer perception model. Multi-layer, all right? We've got 3 layers right here. 1, 2, 3. We've got perceptrons in them. That's what these little nodes are called in each layer. And deep learning is considered deep when your aforementioned model has got more than the input and the output. It's got this hidden layer in the middle. So, essentially, what this big, scary graph in the middle is, that's our function. That's how we're going to learn. We're going to put in our inputs, think things like steak, salsa, Sour Patch Kids. And on the output, we're going to say, is this burrito good or bad? Now, I didn't do my project on burritos. I did it on like network traffic, right? We'd have things going in like flags, the length of the message, just like Wireshark capture. And so there were 83 inputs there. And on the output, we'd say, is this benign? Or is it one of these like 5 different types of attacks? So a little bit more complicated, but let's run through the process if we're talking about a burrito thing, right? So step 1, we're going to put in our labeled data that we talked about earlier, right? Things like what we're putting in the burrito, and things like, is this a good burrito? Is it not a good burrito? We're going to add some small randomness to our function. So on step 1, right when we boot up the neural network, we're going to say, put in all of our inputs. Like the function's random, it doesn't know anything. So it's just going to do some random stuff to it, and it's going to guess, is it a good or a bad burrito? Next up, it's going to figure out how close our guess was and compare it to the actual output from. Let's see. Oh yeah, you can't really see it, but we're going to compare the output from our function to the output in our labeled set. We're going to make changes to our function because it's going to figure out like what inside this network made it do well, what made it do not well. We're going to make some small changes, and you're going to rinse and repeat like a gazillion times. Now, here's like a model for how the whole thing works. So like I said before, we had our inputs, our outputs, our labeled data, and starting, right? We're going to pre-process that data because like, as much as I would love to actually put like Sour Patch Kids inside the machine learning algorithm, Like computers don't eat those; they eat zeros and ones. So we got to turn that into something you can eat. We're gonna put it through the preprocessor, which actually I was surprised to learn that's like half the work of making a machine learning data model. You gotta preprocess all your data in a way that it can read. So we're going to use that data for the training process. This whole thing right here, we're going to train the neural network, and then once that's all done, once it has like an okay idea of what we think a good burrito is, we're going to put in just some inputs, no outputs. Imagine like we're giving it some ingredients, right? We're testing out something new. Let's say we're putting in airheads, we're putting in some chicken, we're putting in some canned beans. It's going to go into the neural network, and it'll use that approximate function. Sorry, it's literally captions. And come up with an output. And that's what we're using this for. It's going to find data it hasn't seen before, and it's going to give you good guesses. Now, let's talk a little bit more about pre-processing, because I haven't touched on it yet, and it was a really big part of the project. So like I said, the model cannot take strings, cannot take Sour Patch Kids. It needs to be nice numbers, things like integers, floats, etc. And if numbers are really large or really small, they might be overvalued or undervalued. And so let me show you what the data set had. It was really bad. Like there were labels along the top. There were like infinity values. There were not a number values. Like the labels, you can see them on the right side of the left there. Things like the 9. They would be strings, so I had to turn those into numbers as well. And it's just a pain, but it was a big part of it. So let's move on to the demo. Should be pretty neat. Let's see. Shall we? All right. So first thing I'm going to show you guys is this thing right here. This file, WednesdayWorkingHours.pcap_iscx.csv. There we go. All right. So this CSV file, I don't know if you can hear, but my fan is just going crazy. It's trying to load it. This is what it looks like. It's hefty, right? It's got all these different like Wireshark packet capture data points. And so along the top, we've got all sorts of different things like source IPs, source ports, destinations. We've got total length of packets. We've got flags. Like everything you've ever heard in like your networking classes is in here. All that. And then down below, we've got values for all these things. And there's a lot of them. It's a big data set, but that's good because we need a lot of data to train the model. It actually goes down to like 690,000 of these, which is pretty crazy. It's a lot. Like, dang. So, yeah, I was talking about that preprocessor. There's a few different things I did when I was preprocessing it, right? We had to change strings to processable data. Some people opted to get rid of things like IP addresses or timestamps. I chose to keep them because I think like if attackers are always coming from a certain network or they're attacking at a certain time of day, that could be valuable information for the machine to know. So we change like any of those strings to like indexes. We'd go through, we just process it, right? And once that's all done, we'd end up with a bit nicer of a file like this one. Sorry, it's still got a lot of rows. It's going to take a minute to load. The word stays, I swear. There we are. Okay. Yeah, this has a lot of pretty much like the same data, but it's got a few things applied to it. We've gotten rid of strings. Everything is just a float now, and we've normalized it, or basically turned everything from a number to 0 to 1, so that no data point sort of outshines the rest. There's some things like packet length, where that'll be like a brilliant, it'll be a really big number, and it'll just make all the other data points seem like nothing, and it wasn't learning. Sorry, but let's get back to the model. I'm going to run it. I'm going to open it up in debug mode, right? And basically, we're loading in that data set. It's going to take a minute to load it all because, like I said, there's like 600,000 things. And while that's loading, we can go down here, and I can show you some of the parameters we're using, all right? So we're going to do 10 epochs. And what an epoch is it's one run through all that data. So one run through all those 600,000 entries. A batch is, or a batch size, I guess is a better way to put it. It's how many entries it's going to go through before the machine stops and it thinks, all right, let's reconsider our function. Let's change up some weights. Let's do some Back propagation, another cool buzzword. So, another thing to note, can take a look at the model I built here. Where are you? Here we go. So, if we think back to like the presentation, it had like 3 input nodes, 3 hidden layer nodes, and then 1 output node. Right here, we've got 83 input nodes, 12 in the hidden layer, and then 6 on the output, and that's because we had those 6 outputs. Let me turn on high performance mode. Really suck up that juice. Oh yeah, crank it up to 10. All right, so you may note that I only used around 10 epochs here. That's just for the demo. Normally you'd run this for about 1,000 times and it'll take like 15, 30 minutes. But yeah, pretty much. All right, we're gonna give it one more restart, and if it doesn't work, that's too bad. But it should be good. I believe in it. Come on. All right, in the meantime, you can check out some of these references. Unless it's doing something. Let's see. No, not quite. Give it a minute. All right, yeah. So at the top there, that's my information if you want to know a bit more about the project. You've got Dr. Bo Yuan's email right there if you're interested in taking the class, learning more about it. He's very knowledgeable. I used PyTorch for my model. We've left the documentation there, but you can use things like TensorFlow. I know there's a lot of other resources that people have chosen. There's that cool site there, playground.tensorflow.org. You can quickly simulate your own model just to learn about how multi-layer perceptron works. And then down at the bottom is the title of that paper that we had to read. Let's see if it's doing something yet. There we go. All right, so we can see it pasted out just the model structure, and now it's starting the epochs. So first epoch, it'll also give a stat called the latest loss. And that loss is basically how far from a correct answer the model was on that last trial. And if that loss is getting smaller with each epoch, it's learning, it's getting closer. So it's going to do about 10 epochs, and it's going to spit out some statistics about how close it was, how accurate it was, F1 score, all that good stuff. So I'd say a majority of the learning will happen over the first 100 epochs, and it really starts to slow down because there's kind of a limit, right? So total accuracy, we got about 95%. We could figure out whether it was benign or malicious. And then we got some additional stats like the precision, the recall, the F1 score, and all that. So that's the demo. Here's some more references. If you got any more questions or anything, happy to answer them. But that's the presentation. Thank you all. Question?
I have to know.
Yeah.
Can you try the Sour Patch Kids burrito?
I really heavily considered getting one from Salsa's right before my presentation, but I mean we're in the cyber range, so we cancel on that. But maybe some other time. I gotta try it sometime. Yeah. Anything else? Yeah.
You said that for machine learning, it's kind of like determining the trends that happen in mental journey. You determine it. It's like kind of like a random guessing check. How does like in practice it work in college, whether it's like something that's good or bad?
Yeah. So if you remember that loss, the loss is like how far from the right answer it is, right? And the goal of machine learning is to minimize that loss by whatever means possible. So basically, let me go back to the other slide. Yeah, so we're going to put in our input data. It's going to come out with like a score of whether it thinks it's like a good or a bad burrito. And we could say like the machine spits out like a 0.6, which means like 1 is a good burrito, 0 is a bad burrito. It thinks it's a pretty good burrito, but it's like not sure. And then so basically you would take that score, say how correct it is. The loss would be pretty high, but not that bad because it's close. And it would go backwards. That word back propagation I talked about would go through the model and figure out, okay, which one of these weights, which one of these lines contributed the most to that final score, what made it the most correct, what made it the most incorrect. And then it'll basically strengthen the ones that make it right and weaken the ones that make it wrong. That makes sense. Yeah. Yeah, Chase.
So you did this for one of your classes, right?
That's right.
So do you think other students, specifically freshmen, they're talk about some of the projects that they do in their classes?
Yeah, for sure. I think doing projects for classes, doing projects for RITSEC, doing projects on your own. You know, if you're doing it, you might as well make a presentation off it, right? You're getting all these cool RITSEC prizes. You're getting all this cool research cred. You're getting something to put in your resume. So go ahead, do it. Would recommend. Yeah. Questions, Sharad?
How would you go about throwing this against a live target?
Throwing this against a live target? I'd probably go overhand, but yeah, if I was throwing this against a live target, like you mean actively analyzing incoming network traffic using it like a WAP? Yeah, so you could plug it in. I guess the testing was pretty quick, right? So the test data set, it was, I think, around 100,000 lines. It's going to take forever to load, obviously. Oh, not that bad. Yeah, it was 100,000 lines. And when you look at this execution time on the bottom, it was like 0.03 seconds to run through all that. So you could probably do live analysis of traffic with this. Yeah, that's how I do it. So just run the packets through. This is like straight Wireshark packet capture data. So, I mean, I'm not that good with like the APIs and stuff. So if you figure that out, you can do it for sure. Yeah, it's pretty clean with coming up with results and such.
I can kind of see that with it only being 100,000 lines with being quick, but then how can it check its accuracy if there's nothing saying, like, for this you hard-coded what is malicious, what is malicious, and what isn't malicious. So if it's live, like, if it's going on and you don't know what is and what isn't malicious, and that's why you're trusting the tool to do it, how would it do that?
Yeah. So that's a really good question. Are you sort of saying, let me try to rephrase it right. Would you say that like, oh, it only knows what's malicious and what's not malicious based on what it's seen, right? Yeah. So one of the things we do, there's that original data set, right? But we split it into a training set and also a testing set. And the machine never sees the testing set until it's time to test. And so it trains on this training set. It's just like a random, usually like you save around 10% for testing and you train on 90% of the data. And then, so those stats on the bottom, that precision recall F1 score, like 92 to 95%, that's all on data it's never seen before, completely new. So you could use this on new data. Yeah. Anthony?
Is it a class? Is it kind of just like, oh, here's the second assignment, get thrown into it, or is
This was the first assignment. We got thrown right into it. It was like 2 weeks in, so it was scary, but we got it done.
there's like a lot of like go home and learn this stuff?
I would say so, yeah. Yeah.
Would you recommend the class?
Do I recommend the class?
Yeah.
I mean, Kenny's nodding his head no. I mean, yeah, it's good if you need like a push to really do some of your own projects, do your own research. And if you're down to do that for a grade, then it's good. But the content inside the class tends to be a bit more theoretical and the projects are a bit more practical. So if you're down to be independent, do your own research, figure out how to actually use your own tool, it could be a good class for you. All right. Thank you all.